Hi, this is Steve Denenberg. In this video, we are going to talk about friction. And like most of AP Physics 1, there are going to be a couple of important concepts and then a whole bunch of 8th grade algebra. But the concepts are important. So let's talk about friction. Let's say you have a box, a 20 kilogram box, on the floor of your kitchen. And you apply a force to the box. You put your finger on it and press lightly. Well, nothing happens. The box doesn't move. But what's going on? What is the free body diagram for this box? Well, gravity is pulling down on it by mg, and there's a normal force on the box that the floor is pushing up to balance that so the box doesn't move vertically. But you're putting a force on it. So the box should be accelerating to the right. Why isn't it? Well, the answer, of course, is friction. The floor is applying a friction force that is opposing your applied force. And it balances the forces horizontally on this box so the box doesn't move, it doesn't accelerate. So this is the force of friction. But there is a limit to how much force friction can apply to the box. If you keep pushing and pushing and pushing, eventually the box will start to move across the floor. So here's your floor and there's the box. And now you've succeeded in moving the box, you're applying a force, and you are pushing the box across the floor of the kitchen, but it's moving at a constant speed. It's not accelerating. Doesn't a force cause an acceleration? Well, what's going on there? Well, friction is applying a force that is still balancing the force that you are applying to the box. So yes, you pushed hard enough to overcome friction, and now you're actually moving it across the floor, but you backed off on your push and you're only pushing it hard enough to exactly overcome the friction forces, and the box is moving with a constant velocity. The friction force of friction is how I'm going to write it, is proportional to the normal force on the object. And what is the normal force? If you have an object sitting on the floor, it has a certain mass m, and gravity is applying a force to the object of mg, but the box is not accelerating vertically because the floor has provided a normal force. The floor is pushing up on the box with exactly the same force, so the vertical forces on the box are balanced. This is the normal force. The normal force is the force that is applied to the object by the surface on which it sits to constrain its motion. This box's motion is constrained. It's not going to fall through the floor. So gravity can pull harder and harder. The floor will push harder and harder on the box to keep the box from accelerating vertically. And the normal force is always perpendicular to the surface that is applying it to the object. That's what normal means. Normal means perpendicular. If you have some graph and you have a curve, you might have a tangent to the curve that is like this, but the normal to the curve at that same point is perpendicular to the tangent. Normal means perpendicular. So the normal force is perpendicular to the surface on which the object is sitting. This is easy stuff so far, folks, and it's not going to get any harder. Okay, so we said that the friction force is proportional to the normal force. But what is the proportionality constant? Well, it's called mu, and that's the coefficient of friction. And here we're going to be talking about the coefficient of kinetic friction. Kinetic means moving. We're going to talk about the friction when the box is moving across the floor or across wherever it's moving. And we'll talk about that first. So the friction force equals the coefficient of friction, and here it's the coefficient of kinetic friction times the normal force. And that's the force that is opposing the motion of that box as you push it across the floor. The coefficient of kinetic friction is always between 0 and 1, and it depends on the two surfaces. If it's an ice skate on ice, the coefficient of friction, which controls how much friction there is, will be quite a bit less than if it's a rubber-soled shoe on a wooden floor. Generally, the rougher the surfaces, the bigger the coefficient of friction. So let's go back to you pushing that box across the kitchen floor again. Here's the box. Gravity is putting a force on the box. The normal force we know is the same as that right now. It won't always be the same as that. You're putting a force F on the box, that's U, and friction is applying a force that we now know equals the coefficient of kinetic friction times the normal force, which in this case is the coefficient of kinetic friction times mg, which is the normal force in this situation. Now, this is all the stronger that friction can do. It can't apply a force any stronger than that. If something is moving, this is exactly the force that friction will apply. So if you increase the force that you push on the box with, then the box is going to accelerate by the equation that we know, F equals ma. So the net force will equal the mass times the net acceleration. So what is the net force on the box? The net force on the box is the force that you apply minus the force that friction is applying. So that's the net force on the box, and that will be the mass of the box times the acceleration of the box. F equals ma is one of those equations that will save you frequently in this course. And all we did was draw a free body diagram, figure out what the unbalanced forces are, and we can come up with the equation of motion. So that's easy enough. A couple other points about that. Here you are pushing the box again. You're applying a force. There's a normal force that we know as mg, and friction is applying a force that is the coefficient of kinetic friction times mg. The coefficient of kinetic friction times the normal force. Let's write it like this. The coefficient of kinetic friction times the normal force, because it won't always be mg. Well, it looks like if you increase the normal force, then friction can apply a greater force to oppose your motion. How would you do that? Well, how about if somebody sits on the box while you're pushing it across the floor? Then gravity is pulling down on the box and person with a force of g times the mass of the box plus the mass of the person, and the box still doesn't have any vertical acceleration, so the normal force now equals the previous normal force plus the mass of the person times gravity. The normal force has gotten much bigger, and so the friction force has gotten much bigger, and now it's much harder for you to push the box across the floor. If this were a frictionless surface, of course, you'd be pushing the box with some acceleration, and when someone sat on the box, if you didn't change your force, well, the mass went up, and of course your acceleration would drop quite a bit. But here we're talking about a different situation. Here we're talking about a situation where friction is opposing your motion. If any of this isn't crystal clear, you've got to email me or put a comment below the video. All right. So we said that friction, the force of friction, is always, I'm going to write this out, always parallel to the surface. That's how friction works. And we said the normal force is always perpendicular to the surface. To the surface. So what if the mass is sitting on a wedge? Physicists love wedges. Okay, so here's our mass. And gravity is pulling on the mass. Gravity pulls toward the center of the Earth. And the friction force is going to be parallel with the surface, as it always is, opposing the motion of the mass. But the friction force is proportional to the normal force. And the normal force is the force that is perpendicular to the surface of this angled wedge. But we know how to figure that. The mg that gravity is pulling on the mass with comes in two components. It comes in a component perpendicular to the surface and a component parallel to the surface. So we divide the force of gravity into these two components, and the normal force on the mass matches the component of gravity that is perpendicular to the surface of the wedge. This is the normal force. And the maximum friction force will be the coefficient of friction times the normal force. Here's our angle theta. And we know there's some sines and cosines floating around. Do you remember my foolproof way of figuring out which is which? You start out by drawing the wedge with a very small angle. And here's the mass. And there's a component that's perpendicular to the surface for gravity, and gravity is delivering a component that's parallel with the surface, and those two sum up to gravity being straight down toward the center of the earth. Well, we know if the angle is teeny tiny, here's our unit circle, if the angle is teeny tiny, then the cosine of that angle is just about equal to 1. And in this scenario, we know that the component of gravity perpendicular to the surface is going to be most of it. So that's going to be mg cosine theta. Because mg cosine theta here is almost exactly mg, and the component parallel to the surface is going to be mg sine theta. So when we have a bigger angle, we don't get confused. This component that's perpendicular to the surface is mg cosine theta, and thus the normal force is mg cosine theta. And gravity will have a component parallel to the surface that is mg sine theta. Now that's a lot of marking and drawing, but it's just to make sure that you understand how trivial this all is. Did we lose track of the point? No, I hope we didn't. The point was that the friction force that will be applied to the mass is proportional to the normal force that's perpendicular to the surface and not to the mg that is pointing straight down toward the center of the earth. Now here's another point that we should mention. You have your mass on the surface. Gravity's pulling down with a force of mg. The mass is not accelerating vertically, so the normal force on the mass from the ground is also mg, and the vertical forces are balanced. Do these two forces constitute a Newton's third law pair? For every action, there is an equal and opposite reaction. This is mg, this is mg, the mass is not moving. That's because of Newton's third law, right? Answer, absolutely not. Definite no. And if you're not 100% on that, then you better go watch my playlist series on Newton's laws. So let's do a problem. You have a skier going down a mountain. Oh, there's that wedge that the physicists love so much. So here's my skier going down the mountain. He's heading this way, and he weighs 62 kilograms. I'm sorry, his mass is 62 kilograms. Did you catch that? Now we are told that the friction force opposing his motion is 45 newtons. Okay, you want to do the work force, we'll take it. So 45 newtons equals the friction force. The angle of the mountain is theta, and the skier is coming down the mountain, and the question is, what is the coefficient of kinetic friction between the skier and the snow? Well, we kind of just did this just a little bit above. Let's figure it out. Here's our skier. And what are the forces on the skier? Well, we know gravity is pulling straight down with mg on him. But really the two components of that are perpendicular to the mountain, which is mg cosine theta, and parallel with the mountain, which is mg sine theta. The skier is not accelerating down into the mountain itself, so the mountain is providing a normal force on the skier, that is mg cosine theta, to match the component of gravity that is perpendicular to his surface. And this is the normal force, like I just said. So the friction force, as we know, equals the coefficient of kinetic friction times the normal force. Are we done with the problem yet? The friction force they gave us, 45 newtons. The coefficient of kinetic friction we're supposed to find, and the normal force we just saw was mg cosine theta. So now this is 6th grade algebra. So we have the coefficient of friction equals 45 newtons divided by mg cosine theta. And since m is 62 kilograms and g is 10 meters per second squared, we have this equals 45 newtons divided by 620 newtons times cosine theta. And I guess I didn't give you theta. And we said that was the coefficient of kinetic friction. Now check this out. On the top we have newtons, and on the bottom we have newtons, and a trig function doesn't have units. So the coefficient of kinetic friction does not have units. It's like radians, it's like the cosine of an angle. But that makes sense, doesn't it? Because we said the friction force equals the coefficient of friction times the normal force. Well, this is a force measured in newtons, and this is a force measured in newtons, so this cannot have its own units. And let's do that even easier. You're back to the kitchen. You have a box that is 10 kilograms. You're pushing on the box with a force of 50 newtons. The box is moving across the kitchen with no acceleration. And the question again is, what is the coefficient of kinetic friction? Well, let's draw our free body diagram. Gravity's pulling on the box with mg. We know our normal force is mg. You're pushing with 50 newtons. If the box is not accelerating, there should be no net horizontal force on the box. So we know that the friction force, which is applied at the surface parallel to the surface, better be 50 newtons. So we have the friction force is the coefficient of kinetic friction because it's moving times the normal force. We've figured out that the friction force better be 50 newtons. We know that the normal force is 100 newtons for a 10 kilogram box. So the coefficient of kinetic friction is 1/2. Now we're going to do another little twist on this before we move to the coefficient of static friction. We have our wedge again. This is theta. The mass starts at the top of the wedge, and the coefficient of friction is mu of k. And the mass is going to slide down and come to the bottom. And the question is, how long will it take to slide to the bottom? Well, let's just start all these problems like we always do. Let's write down what we know. We know that gravity is going to pull on the mass with mg. We know that the perpendicular component of that is mg cosine theta. So we know that the normal force is mg cosine theta. We know that friction is going to be opposing the motion of the mass with the force of the coefficient times the normal force. So the friction force here is mu sub k times the normal force of mg cosine theta. Well, gravity also has a component this way. So gravity, besides pulling into the surface like this, is pulling along the surface. And this is mg sine theta. So the net of the two forces on the mass sending it down the surface are mg sine theta from gravity heading toward the destination, and then there's a friction force of mu sub k times mg cosine theta that's trying to push it back up to the top. So assuming it actually slides, the net force is mg sine theta minus the coefficient of friction times mg cosine theta. And oh, guess what? F equals ma. So if we take the force and divide it by m, we get the acceleration of the mass as it heads down. So the mass's acceleration equals g sine theta minus mu times g cosine theta. All right, so we know something's acceleration. We know how far it's supposed to go. Oh, do we? I didn't give that to you. Sorry, my bad. Let's say the run is a distance d meters from where he starts down to the end of the hill. Well, now we're back to the very first playlist in this series on AP Physics 1. If you have a constant acceleration and you know how far something is going to go, we have this equation. We have distance equals the initial velocity times the time of travel plus 1/2 times the acceleration times t squared. Remember this? This is the very first equation on the page of equations that they give you to start the test. Well, v sub 0 is 0 because the mass begins with no velocity. So we have d equals 1/2 at squared, and 2d equals at squared. 2d over a equals t squared, and t equals the square root of 2d over a. And what is a? We just figured out what a is up here. So plug this into here, and that will give you how long it took the mass to slide down to the bottom of that wedge. See, all you have to do is understand what's going on and then do the simple algebra. Okay, so what else is going on? Let's go back to that 20 kilogram box on the floor of your kitchen, and you touch it with the finger and apply 1/10 of a Newton to it. And we already said it wasn't going to move. But you keep pushing, and eventually there's a limit to what friction can apply to it, and the box will start to move. Well, when a box is not moving, when it's not in motion, we have an equation that describes what's going on, that we say the force of friction equals the coefficient of static friction times the normal force. When the force that you apply to the box overcomes the maximum possible friction force, the box will start to move. So really, this is not the accurate equation. What we should say is that the force of friction, when the box is not moving, is less than or equal to the coefficient of static friction times the normal force. Because if you're only pushing on it with 1/10 of a Newton, then the friction force is only going to be 1/10 of a Newton. It's just going to balance what you put on it. And the more you push, the more force friction will apply so that the box doesn't move. And you've experienced that. But once you push hard enough, friction can only give you this much. When you overcome that, the box will start to move. This is also dimensionless. It is also typically between 0 and 1. and it is also proportional to the normal force on the box from the surface that is perpendicular to the surface, and friction is still always parallel to the surface. Now here's something else that you have noticed, and you know it instinctively. You're pushing on the box, and you push harder and harder, and you really have to push to get it to move, but then it starts moving, but then you don't have to push quite so hard to keep it moving. Why is that? And that is because the coefficient of static friction is usually greater than the coefficient of kinetic friction. When the box is not moving, friction can produce a greater force to keep the box from moving than friction is able to apply against the motion when the box is actually moving. So there's a little chart that you may see that if here's the friction force between a mass and its surface, and here's the applied force that you're putting on it. So this is you pushing on the box, and this is how much friction is pushing back on you to try and keep the box there. As you apply more force, the box doesn't move. Friction will keep up with you. At some point, the box will start to move, and the chart will look something like this. The friction force can get greater and greater the more you push on it. But when it starts to move, the maximum friction force that it can apply is less, because it depends on the coefficient of kinetic friction, whereas keeping the box from moving depended on the coefficient of static friction. So let's do a different kind of a problem. And guess what? We're going to have a wedge. So we have a wedge with an angle of theta, and we have a mass sitting on the wedge, and it's not moving. The coefficient of static friction is high enough to keep this mass from sliding down the wedge. And the question is, if we start raising theta, if we put this at a higher and higher angle, how high can we get before the box slips and starts to slide down the wedge? Well, like every other problem, you write down what you know. Often it starts with the force body diagram. So let's write down what we know. We know that gravity is pulling down with mg, that the component perpendicular to the surface is mg cosine theta, that the component parallel to the surface is mg sine theta, and that the normal force that's keeping the box from sliding into the wedge is mg cosine theta, matching gravity's contribution. Well, gravity's trying to slide it down, so something is balancing that force and keeping it from sliding down, and that's friction. Friction is opposing the applied force or the motion. Here there's no motion, so friction is opposing the applied force that gravity is putting, trying to move the block along the surface. And so friction is pulling up on the box with the same force, because they have to balance to keep the box from accelerating down the slope. But if this is the friction force, we also know that the friction force is what? The coefficient of static friction times the normal force. And here that's U sub s, and the normal force is mg cosine theta. Here's the normal force right here. And because gravity is pulling down the slope this hard, and friction is opposing that this hard, we know that the friction force equals mg sine theta too. So let's write it out. The coefficient of static friction times mg cosine theta equals mg sine theta. Let's see what happens. Let's knock out the m. Let's knock out the g. Let's divide both sides by cosine theta. Well, look at that. The coefficient of static friction equals the tangent of the angle of the wedge. Isn't that interesting? So for example, if the coefficient of static friction is, let's say, 0.9, then the maximum angle you can hike the wedge up to before the mass slips, theta, will be the arctangent of 0.9, which is 42 degrees, because tangent of 42 degrees is 0.9. So look at this. We said that the coefficient of static friction or kinetic friction doesn't get higher than 1. And the angle with the tangent of 1 is 45 degrees. Does that mean that anything will slip if you raise the wedge higher than 45 degrees? Well, yeah, probably. Actually, you can get a coefficient of static friction that's higher than 1. Picture the two surfaces of Velcro. But that's really a different thing. That's those little plastic hooks in the Velcro and not the interaction of the molecules on the two surfaces. Now, if you were really paying attention, this might bother you just a teeny bit, because you'd say, really, is this as high as it can get? How do we know in this situation friction is giving everything it can possibly give? Well, it's because we said that for our analysis, the friction force would be the coefficient of static friction times the normal force. And as we knew from before, the possible strengths of friction with the non-moving box are less than or equal to the coefficient of static friction times the normal force. So if for our purposes we say it's equal to that, then we're saying, yes, that is the maximum possible force that friction can apply in this situation. Compare these two situations. You have a mass, you're pushing harder and harder to find out how much force friction can apply, and you see what your applied force is when it starts moving. Then you try the experiment again with a box that has the same mass, but it's a much bigger box. Is the friction force going to be larger in this situation? And the answer is no. The friction force equals the coefficient of friction times the normal force. And gravity's pull on these two masses is offset by the same normal force, and the surface area of contact doesn't matter for our purposes. Before we end this video, I think we should look at one more situation. Once again, we have our wedge, and we have a mass sitting on the wedge, and it's not moving. Here's our theta. The coefficient of static friction is mu of s. And the question is, how strong of a force do we have to apply in the upward direction to the mass to get it to move? Well, let's see. We know that gravity is putting a force on the mass in this direction of mg sine theta. And we know that the normal force on the mass is mg cosine theta. And if the mass is just sitting there, then the friction force on the mass is offsetting gravity. And the friction force is mg sine theta in this direction. That's the friction force. This is the force from gravity. Now we know that the friction force always opposes the applied force or the motion of the object. And we can say that the applied force here is gravity. Gravity is trying to slide the block down the wedge, and the friction force is exactly negating that, so there is no net force along the surface, and the mass does not accelerate, it doesn't move. But what if we apply a force to the mass in the upward direction? If we apply a force offsetting gravity, then the forces are balanced, and the mass stays put, and there is no friction force. But then once we increase our applied force beyond here, then our force has overcome gravity and is trying to push the block up the wedge, and now friction will develop a force in this direction to oppose us. And what is the maximum force that friction can apply? Well, the maximum force that friction can apply is going to be the static coefficient of friction times the normal force. So in order to get the block to move up the wedge, we have to overcome gravity, and we have to overcome the force that friction can put in the downward direction to oppose us. So what kind of force do we have to apply? The gravity component is mg sine theta, and the friction force that can be generated against us is mu sub s times the normal force, and that equals mg sine theta plus mu sub s times the normal force, which is mg cosine theta. And that's how hard we will have to apply a force to that mass to get it to move up the wedge. We will conclude our discussion of friction in the next video, where we will discuss energy considerations for the force of friction. See you then.